Okay, you can hear me. That's good. Okay, so in this section, we're going to take a look at logarithmic functions. In the last section, we had taken a look at logarithms and their properties. We had taken a look at the product rule, which states that you can rewrite a sum as a product and a product as a sum. We took a look at the quotient rule, which allows you to write a quotient as a difference, and we also took a look at the power rule. Now, there are some sister rules that are using what are called the natural logs. We talked about the two types of logs. The common logs, they have an understood base 10, and a natural log, they have the understood base e. Okay, so here we're looking at just the graph of a log function. So notice here the base is not necessarily 10 or anything like that. The base is variable. Here we're just noticing the shape of a logarithmic function. So here we have our function f of x. I'm going to blow this up a little bit. Is equal to the log base a of x. And keep in mind that a has to be greater than 1. So when we were converting from logs to exponents, right, your base of your log has to be greater than 1. And also your exponent has to be greater than 1. So just notice this is the general shape that our log takes on. It should pass through the points 1, 0. It should also have the points a, 1. Here again, a is the base. It will also pass through the points a to the negative first power, negative 1. So here again, we will pull a from our base. And just some more information about it, it's always increasing. As you read this graph from left to right, it increases, and its domain is from 0 to infinity. Here we have the graph of a log function if your base is in between 0 and 1. Okay, so your base, it can be negative, right? It has to either be greater than 1 or it has to be between 0 and 1. Notice that if your base is in between 0 and 1, this is the shape your graph will take on. And as you read this graph from left to right, notice that it descends, right? It's decreasing. It should pass through the points a, 1. Okay, here again, a is your base. It should also pass through this point, a inverse, negative 1. Now, how will you actually graph these logarithms using a calculator if there's something other than a base 10 or a base e? And also, how would you use a calculator to calculate a log that's not a base 10 or a base e? So I'm going to go back to the document camera. Well, I guess actually before I do that, I'm going to pull up the homework. And I just want to look at a couple of sections. Now, seven. All right, so while this If you have your calculator for these next few problems. Okay, I don't quite know where I left off. So I'm just going to go back 1 second. All right, so I believe we were talking about logarithms whose base are in between 0 and 1. They would take this particular shape, right, and they would pass through these points. As far as our calculator is concerned, we have the capital log log, which are logs that are common logs and have a base 10. We also have a ln or natural log, which are logs that have a base of understood e. And I posted a video that kind of goes into that exponential e concept and the relationship between the exponential e and the natural log. Okay, so I want to take a look at, I believe it's problem number 11. Okay, Okay, so how would we evaluate a log such as this? This is the log base 16 of 64. And I want to use my calculator. However, right, my calculator can only deal with common logs and natural logs. Well, there's something called the change of base formula. And here is the change of base formula. Okay, I actually just wanted the formula, not a video. So we just kind of take this. I hope everybody can see this. This is the log base B of A, right? So here in my initial log, my base is B. The argument of my base is A. I can rewrite this using the change of base formula as the log base X of A. So I'm taking my argument, okay, I'm sort of leaving it as my argument, but I'm changing the base to X, divided by the log base X of B. So in this denominator, I'm taking my base, I'm rewriting my base as an argument, and I'm changing my base to X. And here's what sort of pulls this off. Just notice that for my bases, they must be the same base. So my bases can either be base 10s or they can be base E's, which will allow me to use the calculator. Right? So keep this formula in mind. So I'm going to go back to our problem. So we have, and it may be helpful for me to actually write this out on camera. All right, so here was our change of base form. It was log base B of A. That's equal to the log base X of A divided by the log base X of B. Right, and here was our question. We were asked to evaluate log base 16 of 64. So using our change of base formula, I can rewrite this as the log, and I'm going to use a base 10, so I'm not actually going to write a base. It should be understood to be 10. I'm going to write this as the log of 64 divided by the log of 16. So I'm going to put that into the calculator. So I'm going to put in the log of 64. I'm going to close off my argument divided by the log of 16. Here again, I'm going to close off my argument. It wants me to put this in as a simplified fraction, but notice the calculator gives me a decimal of 1.5. In order to convert this to a fraction, I'm going to press math. And the very first option is the command to take what it's given and convert it to a fraction, which is what I want. So I'm going to hit enter. I'm going to hit enter again, and we get 3/2. All right, now there's something else I want to show about the formula. You may actually see the formula written in a different manner. And so I'm going to switch to the document camera. And you may also see the same formula written like this. You may see ln A divided by ln B. And this will also work, which means I could rewrite the log base 16 of 64 as a log of 64 to log of 16. So here I've changed both of my bases to base 10. Or I could write it as a natural log of 64 divided by the natural log of 16. And I should get the same result, which is 3/2. So I'm actually going to verify that with the calculator. So now I'll put in the natural log of 64 divided by the natural log of 16. And I get 3/2. Okay. Now we saw in the last section that the log of, let's say the log of 64 and the natural log of 64 are two different numbers. All right, so when you're using that change of base formula, just be careful to keep in mind which base you're working with. All right, I also want to take a look at problem number 9. And in this problem, we are asked to graph. We're asked to graph the log base 3 of x. So here again, I am running into a problem. I can only use the common log and the natural log. So how would I use the calculator to graph this base 3? Well, in order to graph it, we will use the change of base formula. So I'm going to switch back to the document camera. So here we have log base 3 of x. So if I want to graph it, I would have to graph it as either base 10s or exponential e's as the base. So here I'm going to stick with base 10. So I could rewrite the log base 3 of x as the log of x divided by the log of 3. And this would give me my graph because I'm dealing with base 10s. I could also graph it as the natural log of x divided by the natural log of 3. So let's go back in and put these into the calculator. So I'm going to put this in as the log of x divided by the log of 3. I'm going to use Zoom 6 to graph. And I have my curve. I could also use the natural log of x divided by the natural log of 3, and I would get the exact same curve. So just as the change of base formula works with common logs and natural logs, so do those properties of logarithms. So just to show an example, okay, so I believe everybody is. So here are the properties for natural logs. And you'll notice they're quite the same as the properties for the logarithms. So natural log of x times y, that equals ln x plus ln y. So this is the product rule. You can write a product as a sum, and you can write a sum as a product. The natural log of x divided by y is ln x minus ln y. So it's just as the same when we're dealing with logarithms. And then there's the power rule. The natural log of x raised to the power of r, that's equal to r times the natural log of x. So we have the product rule, the quotient rule, and the power rule. So let's take a look at a couple of problems. So this one is actually similar to number 8, and this is from 6.5. And we're asked to solve ln x plus ln x squared is equal to 4. So notice in the previous section when we were solving logarithms, the rationale was to convert the logarithm to an exponential function and then solve the exponential function, which is basically the same thing I want to do here. However, I must write everything in this case as one single common log. So that's where those formulas come into place. So if I go back to my formula sheet, this very first formula says that I can write a product as a sum, or I can take a sum, which is two individual terms, and I can write it as a product as one term. So I'm going to use the property, rewrite these two terms as one term, then I'll convert this logarithm to an exponential, and then I'll solve the exponential. So I'm actually going to use the product rule. I can take the natural log of x plus the natural log of x squared, and I can write that as the natural log of x, and I'll put this in a set of parentheses, x times x squared. Right, so the only thing I did here was I used the power rule. So now if I multiply x times x squared, I would have the natural log of x to the third power is equal to 4. Right, so here I use the product rule. I've rewritten the sum as a product. Now I'm going to convert this natural log to an exponential function. So the way we do that is we take the base of our log, which in this case the base is e. The base of that log serves as the base for your exponent. We're going to raise that to whatever our log is set equal to. In this case, is equal to 4. And that's going to equal to the argument of our log, which is x cubed. And now I basically want to solve for x, not for x cubed. So in order to solve this for x, I'm going to raise both sides to the 1/3 power. So e to the 4th gets raised to the 1/3. X cubed gets raised to the 1/3. So this is where I'm really raising everything to the 1/3 power. Because when I raise a power to another power, my operation is to multiply. So if I multiply 3 times 1/3, I get 1, which is x to the first power, which is what I'm trying to solve. Whatever you do to one side, you must do the exact same thing to the other side. So if I raise one side to the 1/3 power, I must raise the other side to the 1/3 power. And here again, if I were to simplify, I would multiply. So 4 times the third is 4/3. So we have e to the 4/3 is equal to x. And this is actually number 8. I'll show that in a second. It seems the system seems slow when I go from my document camera to the actual application screen. All right, let's take a look at another problem. This one is similar to number 9. And here again, we're asked to solve. This is the log base 4 of x plus the log base 4 of x minus 6 is equal to 2. So here again, my rationale is to get all of my logs on one side of the equation, write as a single log using the formulas, change that single log to an exponent and solve the exponent. All right, so I'm going to use that same product rule we used earlier. I can rewrite a sum as a product. So that means I can write the log base 4 of x plus the log base 4 of x minus 6 as the log base 4 of x times x minus 6 is equal to 2. All right, so I'm just multiplying my arguments. So now if I actually multiply, I'm going to multiply everything by x. So I have the log base 4 of x squared minus 6x is equal to 2. So now notice we once had 2 logs, we only have 1 individual log. So I'm going to convert this log to an exponent, and we're going to solve the exponent. All right, so much as we did in the last problem, the base of my log is 4. That means the base of my exponent is 4. I'm going to raise 4 to the second power and set that equal to x squared minus 6x. I'm going to simplify. 4 squared is 16. I'm going to bring the x squared minus 6x down. Notice that this is quadratic. My highest power is squared, so I'm going to set this equal to 0 and solve it. So I'm going to subtract 16 from both sides. So I have x squared minus 6x minus 16 is equal to 0. I'm going to first try to factor it, and I believe this is factorable. I'm going to make 2 sets of parentheses. I'm going to put x in front. Since my last term is negative, one of my numbers has to be positive. One has to be negative. I'm going to use a negative 8 and a positive 2. Right, because 2 times negative 8 is negative 16. But when I add negative 8 plus 2 is negative 6. The next thing I'll do is use the 0 factor property. So I'll set each factor equal to 0. And I'll solve. So here I would subtract 2, so x is equal to negative 2. And over here I add 8, so x is equal to 8. Right, so I have 2 answers. Now we must check our solutions with our original problem, because notice that my introduction on the natural logs, we can't have zeros or negatives. Excuse me, we can't have negatives as arguments. So if I were to check these, first I'm going to check negative 2. So if x were negative 2, that would leave me with a negative argument here, which isn't possible. If this were negative 2, I'd have negative 8, which is not possible. So I want to discard -2. And now I want to look at 8. So here I would have 8, which is positive, 8 minus 6, which is positive. So my only solution here is x is equal to 8. All right, so once we solve, we must check to make sure that our arguments are positive. All right, and I also want to take a look at number 11. We have the log base 8 of 4x minus the log base 8 of x plus 2 is equal to the log base 8 of x. Okay, so here we have 3 logs. So our goal is to get all of the logs on the same side of our equation, rewrite the separate logs as one single log using the formulas, write that single log as an exponent and solve the exponent. All right, so the first thing I'm going to do here is take this log base 8 of x and I'm going to subtract it from both sides. So I'm going to have the log base 8 of 4x minus the log base 8 of x plus 2 minus the log base 8 of x is equal to 0. All right, so how will we write these 3 individual logs as a single log? All right, so notice that from our formulas, we can rewrite any negative logs, we can put those into the denominator. So this is how I'm going to write this out as a single log. This would be the log base 8, and I'm going to put our little division bar for 4x. So notice this is understood to be positive, right? So my positive logs go in my numerator. My negative logs go in my denominator. So here we have minus log base 8 of x plus 2 minus log base 8 of x. So since both of these things are negatives, I'm going to put them in the denominator and I'm going to multiply them by each other. All right, so this is what I have. All right, so notice that in my denominator I have x plus 2 times x. Those things go in my denominator. The next thing I'm going to do is rewrite this as an exponent. So the base of my log is 8. That means the base of my exponent is 8. I'm going to raise that to the 0 power and set that equal to 4x over x squared plus 2x. Right, so I've changed my log to an exponent. Keep in mind from your properties for exponents, anything to the 0 power is 1. So I'm actually going to write this as 1 is equal to 4x divided by x squared plus 2x. All right, so the next thing I'm going to do is I'm going to multiply both sides by x squared plus 2x. So if I multiply my left-hand side by x squared plus 2x, x squared plus 2x times 1 would give me x squared plus 2x. If I were to multiply my right-hand side by x squared plus 2x, it would cancel out my denominator, so that would leave me with 4x. And I'm just going to transfer this up here. So we have x squared plus 2x is equal to 4x. So here I'm going to subtract 4x from both sides. I'm going to factor out x. I want to use the 0 factor property. So I have one solution here, x equal to 0. Here I'm going to add 2 to both sides. And I have x equal to 2. So notice if I go back to my original problem and check, could I use 0? Well, I would have a 0 here, so I can't use 0 as a solution. However, I could use 2. Because if I use 2, it makes all of my arguments positive. So my solution here is 2. All right, so here I'm going to stop the recording.